The following presentation is from PBS Home Video.
Starlight, star bright, which star will die tonight?
Supernova should be coming up right about now. There it is.
Ah, it is. It's a supernova. Look at all the undulations.
Yep.
We've got another one.
In the death of a star, astronomers probe the clash of cosmic forces.
Gravity wins the final battle and the thing collapses to form a black hole.
The strange limits of our universe.
It wouldn't be just the obliteration of all matter and energy, but of space and time as well.
The universe reveals its deepest secrets in a blinding flash. To some, there is no vision more reassuring. The cycles of the sun and the moon, the heavens ceaselessly turning. The night sky is unchanging and eternal, or so it seems. But modern astronomy has given us a much different vision, a universe that roils and vents its rage. Fierce radiation jets that erupt from newborn stars. In netherworlds where matter billions of times the mass of our sun collapses to a single point. In the most violent explosion since the Big Bang, the supernova.
Supernovae are the grandest explosions in the present universe. They put out in a period of 10 seconds as much energy as all of the stars and galaxies and quasars in the rest of the observable universe put together. And the energy is not just a great fireworks display, it also gives rise to a shock wave that propagates through the star, and the conditions in that shock wave give rise to a lot of the elements of which planets and you and I are created.
In the cataclysmic energy of a supernova, astronomers are studying the nature of the universe, its past and its ultimate future. Throughout history, our vision of space has been shaped by a handful of rare exploding stars, visible to the naked eye. In the year 1054, stargazers in North America spotted a supernova near a crescent moon. The same event was also recorded in China, Korea, and the Middle East. In Europe, supernova sightings help dispel the prevailing belief that the heavens are static and unchanging. The astronomer Tycho Brahe saw one in the year 1572. He wrote, "I was led into such perplexity by the unbelievability of the thing that I began to doubt the faith of my own eyes." Johannes Kepler recorded the next one in 1604. in the constellation Serpens. Galileo used it to make his case for a whole new approach to astronomy, based on the idea that change is a fundamental part of the cosmos. Today, when or where the next supernova will appear, no one knows. But as they say, seek and you shall find.
Praising our Savior all the day long. Praising our Savior all the day long. The Lord bless you and keep you. The Lord make his face to shine.
By
on
day,
you.
Reverend Bob Evans preaches the gospel to the devoted faithful in churches near the town of Coonabarabran, Australia.
Now and forevermore. Amen.
But he has another flock he knows just as intimately. By night, he's a backyard astronomer of world renown. Since 1980, he has sighted no fewer than 30 supernovae, more than any other amateur on Earth. On the side of his telescope, he's chalked up the locations and dates of his discoveries. The secret to Evans' success is his familiarity with the night sky. He has thousands of galaxies committed to memory and can spot the sudden brightening of stars within them.
In this particular case, the new star appeared in the middle of the dark dust lane. Back in 1985, a supernova appeared in this galaxy, and this other photograph shows us the supernova here in the ring of the galaxy. I found it with a 10-inch telescope from a spot beside the road near the town of Bathurst, a long way from home.
Once, every branch of science depended on the ranks of amateurs. Today, that's true only for astronomy. Evans' discoveries are a windfall for professionals. Spotting a supernova as soon as its light reaches Earth gives them a chance to study it from its onset. Tonight, Evans is joining the ranks of the pros with an observing run at the Siding Springs Observatory near his home.
There's quite a bright star just west of the galaxy, another one southwest, and then quite a faint star northwest. Yes, it's got a very bright center.
Here, Evans can see deeper into space, but in truth, he prefers his backyard. There, his speed and flawless memory command the 1,000-odd galaxies that make up the local region of our universe. And it's there that he has his best chance at spotting the big one, an exploding star so close and so bright it becomes legend. Only one like that has appeared in the nearly 400 years since Galileo's time. Observers in the southern hemisphere saw it in a dwarf galaxy just beyond our Milky Way. For many astronomers, this was the event of a lifetime.
Supernova 1987A in the Large Magellanic Cloud has been a big adventure for me. I remember on the day in February in 1987 when I got a phone call and somebody said, "Have you heard about the supernova?" It was clear that something big had happened.
Now, more than a decade later, they are still tracking the progress of 87A. Ultraviolet rays bursting from a supernova have caused clouds of gas, expelled long before the explosion, to glow like giant fluorescent rings.
And now we're getting a chance to see the whole star and its neighborhood by using the Space Telescope to observe the expanding debris and the stuff that was in the neighborhood that was really lost from the star before the explosion. So we get a whole chance to check out the theory of stellar evolution and the theory for the mechanics of supernovae by looking at a good case. And 1987A is sure the best case that we've had.
In the brilliant drama of a star's death, we glimpse the violence that ruled its life.
Stars spend their entire life fighting gravity. If there would be no other force, gravity would pull all parts of the star and make it collapse to a point. What the star manages to do is to ignite nuclear reactions at the center of the star, which cause a very high temperature and high pressure. And this pressure gives an outwards force which holds the star against gravity. So only as long as the star has this nuclear energy available, it can really hold against gravity.
Stars the size of our sun can keep the inward pull of gravity in check and burn for billions of years. Not so for a large star. It burns hot and fast and steadily packs its core with denser and denser elements.
And as it evolves, it burns lighter elements into heavier ones. Hydrogen into helium, helium into carbon, carbon into magnesium, and so on, and eventually reaching the heaviest element that nuclear fusion can produce, iron, in its core. And so when you have a mass of iron, about 1.5 times the mass of the sun, it no longer has a source of nuclear energy to hold itself up.
Before it actually blows up, a star is first seized with convulsions. It throws its outer layers into the surrounding galaxy. Eta Carinae is a star nearly 100 times the mass of our sun, and a supernova waiting to happen. It has expelled 2 fiery lobes of gas that stretch 9 trillion miles from end to end. At any moment, Eta Carinae could fall victim to the gravity intensifying within. This computer simulation shows the cataclysm that can unfold within a large star's core. Energy released in the collapse heats the star from the inside out to billions of degrees. Within hours, a pressure wave rushes outward, and the star erupts. Our models of supernova explosions are steadily improving. Now, astronomers have begun to enlist them in the study of even larger forces at work in the universe. For the last week, astronomers around the world have been combing the distant universe for exploding stars. Tonight, with a dozen sightings in hand, a team has come to Hawaii's Mauna Kea volcano. Their destination is the Keck Observatory, and one of the largest and most advanced telescopes in the world.
That's right.
You know,
11's back in the picture again, and 13.
13 is definitely.
And that's very nice because it's
that's
4.
very nice. Yeah. That's a little bit inefficient, you know, going back and forth.
No,
because the setup is,
but I mean, if all we have is half a night or something like that, then we
Right.
can just knock off everything that we can see in half a night.
Leading the study, Saul Perlmutter and Alex Filipinko are here to answer a profound question. How and when will the universe one day come to an end?
Bring it maybe a tad of
A singular explosion, the Big Bang, set the cosmos in motion some 15 billion years ago. Ever since, the universe has been locked in a duel between the momentum of expansion and the inward pull of its own gravity. Cosmologists want to know, will space go on expanding forever? Or will gravity someday bring it crashing together in a big crunch? To answer this question, the team will use exploding stars as cosmic speedometers to measure how fast gravity is slowing the expansion of the universe.
We need to know not only the expansion rate of the universe now, but also the past history of the expansion rate.
Coming out the CCD and getting redistributed.
We think that the universe was expanding faster in the past than it is now, and that's because all of the galaxies in the universe are pulling on all the other galaxies.
To get the data they need, it will take superb viewing conditions. They're in for a disappointment. A major storm is blowing across the Pacific. Now Filipinko has a tough call: to try to launch the study as planned, or cut his losses and merely verify some of the sightings.
The weather is critical because we're looking at objects which are, for the type of data we're trying to get, they're at the tough end of even what this telescope can do. But when the clouds come over, it means that our data are certainly compromised. One of the purposes of the Keck observations was to not only see what kind of a supernova it is, but to see details in the spectra, which no other telescope can do on Earth. Okay, it looks like we're getting ready to open, so let's just go ahead and do it.
The team has just 3 nights at Keck, and each one is precious. As darkness engulfs Mauna Kea, the distant universe is poised to surrender its light to Keck's gaze.
Great. Maybe half the night can be salvaged.
Yeah.
A week trying to...
Hopes are high.
Okay, I'm going to start an exposure. This will be number 69 on the low-res disc.
So your first object is HD 19445.
So that's not so bad.
Can't complain.
So we're at the hairy edge, but we might be able to actually get some good data. Certainly seeing a star this faint coming in so brightly means that I don't think we have a huge thick layer of clouds out there.
Filipinko is looking for a certain type of supernova, one that for most of its life resembled the sun. Our star was born some 5 billion years ago and will begin to die in another 4. Its fate is in stark evidence throughout our galaxy. The sun will swell and become a red giant. Its planets, including Earth, will be swallowed and incinerated. A billion years later, it will begin to convulse and expel its outer layers. Those layers may form a ring of expanding gas, like the famed Helix Nebula. A powerful wind still blowing from the star sculpts the inside of this great halo. In the center is the star's exposed heart. Known as a white dwarf, it is the size of Earth, 1/1,000,000th what it once was. If by chance another star is in orbit around a white dwarf, something extraordinary can happen. The intense gravity of the white dwarf draws gas from its companion. At last, its mass reaches a critical limit. Astronomers can determine how bright this type of supernova should be. The dimmer one appears to us, the farther away it is.
These are the most powerful explosions we know of in the universe, aside from the creation of the universe itself, the Big Bang. Besides being exciting, the power of the explosions makes these objects visible at very great distances, which is what makes it possible for Saul and myself to look for these things and use them to study cosmologically interesting parameters like the expansion rate of the universe and the curvature of the universe. These are among the most luminous objects we know of.
Okay, let's see.
For all Filipinko's grand ambitions, his time is running short. Skies are turning overcast.
Ouch.
Well, there's something there.
All right, so yeah,
There's one trace.
Oh yeah,
There's a
yeah.
trace.
It is the.
Oh, man.
Why is it so much better?
I think there's a cloud passing through our field right now. Yeah, things are not very good right now. They're getting worse.
As much as any telescope, patience is the astronomer's tool. They can only hope the weather clears. In any given galaxy, supernovae are rare events, about one every century. And yet their impact is profound.
I study exploding stars partly because I find the concept that atoms in my body were cooked up inside stars, and especially inside exploding stars. I find that concept to be completely mind-blowing, and I'd like to understand the process by which this occurs in the universe. Really, we're studying our own origins at a very fundamental level.
Exploding stars are the wellspring of life. Evidence abounds in our own galaxy. They seed their environments with carbon, oxygen, iron, and other elements necessary for life. Destruction is by no means the supernova's only legacy.
Aside from just being dramatic explosions and making the heavy elements, supernovae influence their surroundings. The gas and dust that exists between the stars, the so-called interstellar medium, is shoved around by the supernovae. It blows bubbles in them. It can compress clouds that might be ready to form and perhaps trigger star formation.
A star hatchery percolates along the edge of the pinwheel galaxy, 50 million light years from Earth. This massive cloud of gas is lush with regeneration. In places like this, the energy let loose by supernovae stirs the celestial mix. Shock waves from the explosion cause gas to condense, then ignite. Stars are born, sometimes hundreds at a time. An infant star scars its environment with the violence of its birth. As matter collapses inward, jets of radiation burst forth like machine gun rounds. In the fold of our home galaxy, the Eagle Nebula is one of the richest of the great star nurseries. Intense stellar winds have sculpted a majestic castle of gas. Inside these giant columns, stars are being born. Yet for the dying stars that set this process in motion, the consequences are grim. Supernovae leave in their wake a range of bizarre objects. Among them, a tiny, dense ball of neutrons.
You form an object that we call a neutron star, which is something that has the mass of our sun, but a radius of only about 6 miles or so. That is a very compact object. Every centimeter cubed of that mass has a mass of 100 million tons.
Because of its intense gravity, a neutron star is a perfect sphere with a surface like polished metal.
It has the mass of a star, but it only has the size of a city. And the structure of that matter is that it's like ordinary matter, where there are electrons and so on orbiting around nuclei, but with all the electrons sort of squashed into the nuclei and the particles up close together. So something that we think of as incredibly dense, like lead, is really mostly empty space. And if you squish all the empty space out of it and get the nuclei right up next to each other, that's something that has the density of a neutron star.
The existence of neutron stars was first proposed in the 1930s. It wasn't until the 60s that hard evidence was finally detected. Within the remnants of some supernovae, astronomers detected a presence that pulsed with radio signals.
When these were discovered by a graduate student in England in the 1960s, the supervisor thought that they should not announce the discovery for a few months, partly in order to check that it was a genuine astronomical object, but also because of the possibility that this might be an alien signal. And in fact, the code name for the object in the early days was LGM, to stand for Little Green Men.
Aliens it was not. Strange it was. The Crab Nebula is the shell of the same supernova that caught the attention of so many cultures in the year 1054. Deep within, astronomers found a pulsar, a neutron star that spins rapidly, emitting radio waves. Now, scientists are using the Hubble Space Telescope to zero in on the pulsar, the star on the left. It is spewing waves of radiation that have etched circular patterns in the surrounding gas. Yet some dying stars meet a fate that is stranger still. Nature, it seems, has contrived a monster. Early in this century, Albert Einstein speculated about a star with such intense gravity that absolutely nothing, not even light, escaped its grasp. He at once dismissed this prospect as impossible.
The notion that you could squeeze something without limits, right down to a zero size, was considered basically absurd and offensive. And so there was a sort of temperamental reaction against this idea of total gravitational collapse right through until the 1950s.
What once seemed beyond reason now defines the frontiers of science. Astronomers believe that when a large star explodes, enough matter can collapse into its core that it literally exits the known universe.
If the mass of that core is larger than about 3 times the mass of our sun, nothing at the end can stop the final collapse. Gravity wins the final battle and the thing collapses to form a black hole.
Black holes. Welcome to the distant edge of space.
For God's sake! How do you stop it?
For this trip, it's one way only.
Well, it maybe sounds like science fiction. You know that there are tides, for example, on Earth caused by the moon. Where the sea is closest to the moon, it is being drawn farther up, so you get a tide, for example. Now, the same thing would happen if you have an object falling into a black hole, say. The only thing is that because the gravitational force there is so large, the tide will be enormous, so that things will be eventually start to be torn to pieces. In fact, that tidal force increases to infinity by the time you fall into the black hole. So at first, larger objects will be torn, but then smaller. Eventually, even on the atomic scale, atoms will be torn apart, and then nuclei of atoms will be torn apart, even on that small scale. So all matter, in fact, will lose the identity as we know it. And by the time you really fall into the black hole, in fact, we don't even have the right physics to describe everything that will happen.
From our vantage on Earth, we define our universe by familiar criteria. But black holes defy discovery. What, after all, can we detect of objects that emit no light?
The fact is we don't have enough cases where we really know what's going on to be able to study it in the detail. You'd like to know, for example, if the black holes are a little different from the theory. And at the moment, we're just at the stage of finding out whether there are good candidates for black holes, things that we think can't be neutron stars, can't be white dwarfs, can't be anything else. The usual argument for a black hole is somebody shrugging and saying, well, what else can it be?
In 1991, astronauts placed one of the milestones of modern science into orbit. The Compton Gamma Ray Observatory monitors high-energy radiation that pummels our upper atmosphere. In 1994, it picked up a sudden eruption in the constellation Scorpius. Astronomers around the world zeroed in on the source. A network of radio telescopes stretching from the Caribbean to Hawaii recorded a rare specter. This is the object that came into view. Matter rushing into it is sending out jets of intense radiation. This week marks the culmination of a year-long effort to study the object. Teams in 8 countries are simultaneously training their most advanced technology on it to discover its true nature. From a telescope in the Andes Mountains in the heart of Chile, the astronomer Charles Balin was the first to pinpoint its location. Now he's venturing back to the observatory at Cerro Tololo to prove once and for all it's a black hole.
It's the strange objects that always tell you the most about the universe and about science. So if you want to increase your knowledge of how gravity works, for example, you don't look at things falling on the Earth, which we understand. You look at the really, really strong gravitational fields that happen near black holes. And those are the things where our current theories might possibly break down. Okay, Luis, let's make this slew.
No one has ever proven conclusively the existence of a black hole.
West.
If ever there was an opportunity, this may be it.
Okay, so are we guiding?
Yes.
Looming within the dense star fields of our Milky Way, 10,000 light years away, this is the brightest and most spectacular object of its kind. What's more, it's not alone. A normal star circles the object in a dance of death. Gas from the star flows into the object through a disk, while jets of radiation shoot from its poles. So powerful is the object's gravity that the companion star's shape is being distorted and squashed. causing its appearance to dim, then brighten as it makes its orbit.
As it goes around the black hole, we're going to start seeing it edge on rather than side on, so you see less of it, and so it's gradually going to get fainter, because in the time we're watching it tonight, it's going to go from almost side on to almost end on. But that one definitely has promise, don't you think?
Though Balin and his team can't view the object directly, they can study its companion.
If you remember, in Alice in Wonderland, there is the Cheshire Cat. The Cheshire Cat disappears from view and only leaves its smile behind to be seen. Black holes have this property. They disappear from the eye, but they leave their smile behind. They leave their gravitational force behind. And it is by that that we then see them and are able to infer their properties.
And then where's the bright star? Is this it?
To prove that his subject is a black hole, Balin must measure its mass at least 3 times our Sun. The only way he can do that is by studying the effect of its gravity on the motion of its companion.
It takes 2.5 days to make it all the way around, and in order to get that far in that amount of time, it's got to go at several hundred kilometers a second. And so during the time we're going to be observing it tonight, that's about 15,000 seconds, so it will have gone over 1 million kilometers traveled through space in the 5 hours we watch it tonight. Okay, so now let's zoom up on it.
With its every movement, the star reveals the nature of the object that shadows it.
On the first night we were here and getting brighter. And then on the second night, we were down here at the minimum, and sure enough, there was a minimum, and it started to turn around right at the end. And sure enough, the first point comes in just where it's supposed to.
Balin has studied the companion star before, but only during a blinding outburst of radiation. Now the flares have died down,
These two guys.
leaving it exposed in stark relief.
Right?
Okay, I see it. It's this.
And now,
Yeah? So here's the star right where the cross is. And that star is different from all these other stars. All these other stars are perfectly ordinary stars, just like the sun. And this thing here is a double star with a black hole eating its companion. And that's what we're going to be watching for the whole rest of the night here.
A lot of people have trouble trying to visualize the nature of a black hole. They know it's something that's greedily sucking in material. It's something that if you fall into, you can't get out of again. And the question is, how can we make sense of all this? How can we, human beings with our limited imagination, try to get some sort of common sense handle on the nature of the black hole? I think the answer is you can't. That these are circumstances where space and time is so warped that it's entirely outside of any sort of human experience. So the only way we can come to understand objects like black holes is through mathematical exploration.
A handful of numbers, some morsels of data. In a scientist's deliberation, one of the strangest phenomena in nature plays out. A black hole contains the mass of at least 3 suns collapsed to a point too small to measure. This is a realm gravity has severed from the rest of the universe.
So we should probably do an observation.
For 5 painstaking nights, Balin has kept vigil.
So we're going to do an
He has found that the object he's studying is massive indeed, weighing in at 7 solar masses. It is, with little doubt, a black hole.
I like to see these numbers come out on the page, and it's a sort of a combination of doing puzzles with doing a kind of profound philosophical thing. what happens inside the event horizon of a black hole is essentially unanswerable in scientific terms, because we are talking about matter falling out of the universe. And so you come right up against the edge of what science can tell you about the universe and what it can't. And I think that that boundary is where philosophy and religion and all these other kinds of thoughts come into contact with science. And that's an exciting thing for me.
The black holes Balin studies may number in the millions in our galaxy alone. But they are by no means the ultimate showcase for gravity's power. In the heart of the M87 galaxy, 50 million light years from Earth, gas swirls into a truly massive black hole and glows as it heats up. Astronomers clock the speed of the gas as it circles around and measured the black hole's mass at more than 2 billion times that of our Sun. The ancestors of these giant black holes inhabit regions at the limits of our vision, a class of objects known as quasars. They are powerful beacons that take us back to a time when gravity began to draw gas into the first galaxies. A quasar is the product of a massive black hole in the center of a galaxy that is swallowing huge volumes of gas and stars. A flood of blinding radiation erupts.
Not only is this an interesting process, the notion that we could have a black hole of 1 billion solar masses shining more brightly than 1,000 galaxies, that's pretty wild. But these are signposts. These were a phase in the lifetime of infant galaxies, and we can see them to great distances. So they are beacons out there at the edge of the universe showing us when galaxies first began to form.
In time, as they consumed their fuel, quasars like these grew dim, but the black holes that powered them remained. Today, they are thought to loom at the heart of many a galaxy, including our Milky Way.
There are two reasons why black holes are important. One is because it's increasingly obvious that they play a major role in shaping the universe, both at the centers of galaxies and as the remnants of burnt-out stars. And we still have yet to learn a lot about them. But there's a deeper reason, I think, why they're important. The black hole conceals something which is very profound, which is often given the word singularity. This is like an edge or a boundary to space-time. It's a point where space and time, so to speak, come to an end.
As we look out into space, we probe a universe we can see, one whose matter emits light strong enough for our telescopes to record. But there is another side to our universe, one that has evaded our detection. In fact, fully 90% of the universe is unseen and unidentified. Astronomers call it simply dark matter. Mysterious particles, countless burned-out stars or black holes. Whatever it is, dark matter is out there.
There's probably more dark matter than there is visible matter, but we really haven't much of an idea as to what this dark matter is. There are a whole lot of candidates, maybe 30 different types of things that the dark matter might be, and of course it could be more than one of them. And I think that is the most urgent question that we must try to answer. What is the dark matter?
Like a black hole, dark matter can be detected by the influence of its gravity. Astronomers have, for example, measured the speed galaxies move within clusters and found that the gravity pulling them along is simply too great for the amount of matter we can see. So too, spiral galaxies, such as our own, seem to be enveloped within vast, dark halos of matter. Now astronomers want to know, is there so much dark matter that its gravity will one day cause the expanding universe to collapse in on itself?
And indeed, the entire universe may one day implode in this manner. It would be rather like us living inside a gigantic black hole, and then the universe would implode to a big crunch, and this big crunch wouldn't be just the obliteration of all matter and energy, but of space and time as well.
Alex Filipinko and Saul Perlmutter are back at the Keck Observatory. To gauge the chances of a big crunch, they will try again to harness the light of a brilliant celestial beacon, the supernova.
It's certainly looking a lot better than last night at this time.
Yeah. Night 1 was a wash. Night 2 is a gem.
In fact, I think we might have some pretty clear skies at the beginning.
Went from 22.6 up to, we think now, about 22.4.
But it might have been on the rise.
The skies have opened, and now the data begins to roll in.
That's not what you're seeing, yeah.
Well, that's an obvious one at redshift 0.45.
Yeah, look at that.
We're completely destroying these things.
Wow. That's great.
Well, now we can when the weather is good, no one can compete with this telescope.
Tonight, they're making up for lost time.
Supernova should be coming up right about now. There it is. It is. It's a supernova. Look at all the undulations. Yep. We got another one. Oh, man, this is like shooting fish in a barrel, you know? Oh, fantastic.
An object's redshift is what defines the speed it's moving away from us. With each exposure, a spectrograph splits the supernova's light into a range of colors. The team will compare their distant supernovae to nearby ones to see how far their light is shifted to the red. That will show how fast their host galaxies are racing away within the expanding universe.
This is going to really wow people.
Yeah, I know, it's nice.
And if we can get this one really well, the higher the redshift, the more leverage we get for cosmological parameters.
Right, we'll just see whether they confirm the...
To really comprehend gravity's vast influence on the universe, they'll need a wide sampling of supernovae stretching across the depths of space.
You flux calibrated this one, right? So really, we want to rotate a little bit clockwise. So it's minus 6.23. The supernova is right here, so just to the right of this bright star. I see emission lines. We got it. There's some stars on the slit as well. There's one.
Sure looks...
Easy supernova.
Yeah?
There it is. Right? Excellent exposure.
That's great.
Okay,
You see the wiggles.
we nailed it. If it never gets cloudy, fine, we'll do number 12, but if it doesn't... Oh, there's one. Yeah, there's a bit of a calcium one. You flux
deep down inside.
If you look at the pictures here,
the reason many of us are scientists is to experience the thrill of discovery.
Before going up.
Right.
To sit there one night observing and to come to a realization that you're the first person in the world to have understood that particular phenomenon. There's something really gripping about that, and it's something that all scientists who have made a discovery never forget, ever in their lives.
Yeah. Okay, there's H and K. Yeah, let's see what it'll turn. Looks pretty high to me.
Okay, that's
wow.
65,
so let's see what this gives us.
0.65.
0.65.
Right.
Hot dog.
So
that is higher.
That explains what's past, where we've gotten these charts for. So.
Oh, if this is the case, then it beats our 0.61 record.
For this one?
The other calcium line gives the same redshift, so we've got a new record. Yeah.
Wait, this is
This could be an overluminous supernova. 3938.
Slowly, a portrait of the fate of the universe is emerging. It will be some time before this study becomes accepted science, but for now, the results are striking.
From the first half dozen of the supernovae that we've discovered in our very distant supernova search, we can already get some hints as to the answer to how much dark matter is there in the universe. And the results that we have so far suggests that the universe is in fact slowing down substantially, and therefore there is a substantial amount of dark matter in the universe that we now would like to go out and look for.
Peer into deep space searching for clues to its most profound mysteries. The nature of supernovae, the extremes of black holes, the puzzle that is dark matter. These wonders are steadily yielding to our gaze.
In a way, while you're doing the observations, you have to not think about that, or you'll just blow your own mind, and you won't be able to do all the many detailed things you need to acquire the data. And it's afterwards, at 8 in the morning, when you're completely exhausted, and you've finished all the stuff you have to do, and written all these data to some kind of magnetic tape, and you take a deep breath and you go out and watch dawn, that it hits you what it is you've been doing the whole night long. And that's a good feeling in the morning. We as astronomers can really only study the light that comes to us from these distant objects. But that doesn't make them any less real. Yes, I have to sometimes set myself aside to think about the actual giant stars that we are studying, or the exploding stars. They all look like little dots on a screen, or a TV screen, or on a photograph. But they're much more than that. And when you sit down to think about the implications of these faint smudges that we see, and you think that these are galaxies full of hundreds of billions of stars, then they do become very real. And the possibilities for life and natural phenomena in the universe become almost limitless.
The most personal thing that I have taken out of this is this incredible sense of belonging, of having one great river of time, from the birth of the universe, the quantum fluctuations, the formation of galaxies, which made possible the formation of stars, cooked heavy elements, supernovae that shed heavy elements like carbon and oxygen into the interstellar medium, later swept up into the solar system, makes planet Earth, makes organic matter, makes human beings, makes me. It's one very beautifully integrated story from beginning to end.
Today, that story is unfolding still. Exactly how it will end remains a mystery. Our own lives are simply too short to witness the grand transformations of the universe. Often, though, in events visible across the depths of space, we gain fleeting glimpses into its true nature. We scan the firmament, and brace ourselves for what it will tell us.
To learn more about mysteries of deep space, visit us at PBS Online at the internet address on your screen. Funding for this program was made possible by the Corporation for Public Broadcasting and by the annual financial support of viewers like you.
This is PBS.
It's a sport, you know, you're trying to find a comet, a little fuzzy object in the sky before somebody else does. And if it is a sport, it must be the world's slowest sport. It's a little bit like looking for a needle in a haystack, but the needle is moving through the haystack, so you have to look through the whole haystack every night in the hope for finding the needle. Every now and then, everything works just right. Nature decides to put on a really dramatic show, as happened when Comet Shoemaker-Levy 9 smashed into Jupiter. I think the biggest impact that Comet Shoemaker-Levy had was right here on Earth, because a whole generation of people, of children, could look up at Jupiter, which is the brightest thing in the sky at the time, and could say, I was there watching when the comet hit Jupiter. PBS got me to this telescope by introducing me to music when I was a young person. PBS is a part of our experience. It gives us a chance to see Americans at their best, at their most enthusiastic. It gives Americans a chance to show each other what they're passionate about and what makes life special for them.
This is PBS.